All right, so we're going to take a look at some of the derivative rules that you'll be using all throughout the calculus course. And just to look at a quick review, remember that this is your definition of a derivative. And if you're not sure where this comes from, you can refer to a previous video on the definition of a function and related rates. And the notation that we use for a derivative is going to be f prime of x, and that's what this little tick mark up here, that's how you refer to that as f prime of x. This means the derivative, and the derivative, once again, is the slope of a tangent line at a particular point on a function. Now, there are different ways of denoting a derivative. This is one notation that can be used. This is called f prime of x. Another notation that is often used is dy dx. And the reason we use dy dx is because slope is often referred to by delta y over delta x. Or if you remember from algebra, that is y2 minus y1 over x2 minus x1. Delta in math always means change. So this is the change in y, which is y2 minus y1 over change in x, which is x2 minus x1. And so delta y over delta x has transformed into dy dx. That means a derivative or the slope of a tangent line at a point on the function. So like I said a second ago, we have f prime of x, or just a shortened version of that is f prime. Sometimes your function will be given to you as y equals, and so the derivative of that, you would often use just y prime or dy dx. And sometimes they will ask you d dx of a function. So they'll say d dx of x cubed, for example. And this would be in parentheses here. And so that is just another notation for find the derivative with respect to x of this function. And this is the derivative of y with respect to x, and the derivative of the function with respect to x, and so on. All right, so now a differentiable function is a function that is differentiable at every point on its domain. And there are several places where a derivative will not exist. One of those places is going to be a corner. Anytime you have a sharp turn in your graph like this, where it's not a curve down here, but it's going to be a sharp corner, you will not have a derivative at that particular point. Another place is going to be a cusp, and a cusp is when you have a curve coming this way and a curve coming this way, and you can kind of think of it as like the little birds you used to draw when you were in first grade. Another type of situation where you will have no derivative will be when you have a vertical tangent. For example, at this point right here, the tangent line is a vertical line. Now remember that the slope of a vertical line is undefined. And since a derivative is a slope of a tangent line, and the slope of that tangent line is undefined there, then you're not going to have a derivative. And then lastly, that is when you have discontinuities. Now the discontinuity I have shown here is a jump discontinuity, but really any type of discontinuity you will not have a derivative. It might be a vertical asymptote, or it might be a jump discontinuity, or it might be a removable discontinuity. None of those will have a derivative at that particular point. All right, so now differentiability implies continuity. So like I said a second ago, if you have a function that's not continuous, or in other words, there is a discontinuity, that means that the function will not have a derivative at that point. So if a function is differentiable, which means a derivative can be found everywhere, then that implies that your function is continuous. Now, the converse of that is not necessarily true, meaning if a function is continuous, then it is not necessarily differentiable. Example of that would be your square root graph, because a square root graph looks like this. It's continuous, but it is not differentiable at that point down there. All right, and then this notation right here, d2y over dx2, this is a notation for a second derivative. Y double prime is a notation for the same thing, or f double prime of x. These all mean exactly the same thing. And on a second derivative, what you are doing is just simply taking the derivative of your derivative. Okay? All right, so here are the 4 rules that we will use for differentiation. Starting with the first one, the derivative of a constant is always going to be 0. Now, you can think of this constant right here as your function. So think of this as d dx of your function. If your function, for example, is y equals some number, what you get graphically is going to be a horizontal line. And the slope of a horizontal line is always 0. So that's why the derivative of a constant is always 0. All right, so then we have power rule. And for the power rule, it simply means you're going to take whatever the exponent is, bring it to the front, multiply it by the constant that is already there, so that's where the c times the n comes in, and then you subtract 1 from that exponent. So for example, if you have f of x is equal to 3x to the 4th power, then the derivative of that would be 12x raised to the 3rd power. Now, if we explore a little bit more, and let's think about that derivative of a constant for a second. Let's say you had an equation that was y equals 3. You can think of this as 3x raised to the 0 power, because any number to the 0 power is 1, so 3 times this is really the same thing as just 3. Now, if you apply the power rule, you would bring this exponent to the front and multiply it with that 3. So that means the derivative of y would be 0 times 3, or 0. Subtract 1 from the exponent, and 0 times anything is equal to 0. So you can think of this derivative of a constant in the same terms as using our power rule that we used here. All right, so next is the product rule. We have a product rule and a quotient rule. One that is for multiplication, the other is for division problems. So when you have a multiplication problem, one thing multiplied by another, the derivative is going to be the first thing multiplied by the derivative of the second, plus the second times the derivative of the first. And then if you have a quotient rule, then you got two things divided by each other. And you kind of got to memorize this, but don't memorize the letters, just memorize the saying. The saying is, it is the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. So it always starts with bottom times the derivative of the top minus top derivative of the bottom over bottom squared. All right, so let's work through some problem situations here. The first one, if f of x is equal to 9, then f prime is equal to 0 because 9 is a constant. You can also think of this graphically. At y equals 9, you would have a horizontal line, and the slope of that horizontal line everywhere is 0. All right, so the next one, if f of x is equal to 2e to the 9th power, remember that e is a constant. Its approximate value is 2.71828, and a whole bunch of decimals forever. It's an irrational number. And so if we take the derivative, 2 is a constant, e is a constant, so this is just simply a different way of writing a constant. There's no variable involved here, so that's just a constant, and the derivative of that would be 0. All right, next one, this is just a real easy power rule. The derivative would be 3x to the 2nd power, just bringing the exponent to the front and subtracting 1 from that exponent. And the next one is when we have a radical, what you want to do is anytime you have square roots or cube roots or anything like that in calculus, vast majority of the time you are going to go ahead and convert them to a rational exponent. So now when you bring the 1/2 to the front and you multiply a half times the 2, that's going to give you 1. Subtracting 1 from the exponent, 1 from a half is going to give you negative 1/2. Well, that would simplify to 1 over x to the 1/2, or in other words, 1 over the square root of x. All right, so the next one is a situation when you have your variable in the denominator down here. And so whenever you see something like this, you might think, oh, we got a division problem, so that's going to be a quotient rule. Yes, quotient rule could be used, so could product rule. But I want to show you an easier way, and that is just simply to convert this so that you are taking the derivative with respect to x of 7x to the negative 3 power. See, if you just convert 7 over x cubed to 7x to the negative 3, all you got to do is power rule. Bring that exponent to the front. That makes it negative 21. Subtract 1 from the exponent, which will give you negative 4. And you can rewrite that then as negative 21 over x raised to the 4th power. That is probably the easiest way of doing this. Now, we could have done the quotient rule, so let's just practice with that for a second and go ahead and do it, see how it turns out. Quotient rule would be bottom times the derivative of the top. Now, the derivative of the top is the derivative of a constant, which is 0, minus the top times the derivative of the bottom, which would give us 3x squared, over the bottom squared. All right, so now this goes to 0. That leaves us with negative 21 x squared over x raised to the 6th power. You can cancel 2 x's on top with 2 x's on bottom, which will leave you with negative 21 over x raised to the 4th power. All right. And we could also do product rule. And so if we think of this right here as our function and treat it as a product rule, we would have first, which would be 7, times derivative of the second, which would be negative 3x raised to the negative 4, plus the second times derivative of the first, which is 0. So once again, that value is 0. 7 times negative 3 is negative 21, x to the negative 4, which is negative 21 over x to the 4th. So that is 3 different ways of taking our derivative of this function and converting it to a power rule is probably the easiest, because power rule is a very simple way of taking a derivative whenever you can. All right, so the next one, once again, you might think quotient rule, but let's think if we can simplify this a little bit. Whenever you are dividing by a single term, that is the same thing as saying each term in the numerator is going to get divided by that term in the denominator. So this is the same thing as saying 2x cubed over that square root of x, or in other words, x to the 1/2 power, minus 3x squared over x to the 1/2 plus 4 over x to the 1/2. Now, all I have done here, this is still actually just y, this is not the derivative yet. All I did is change what the function looks like. And so the next thing is we can simplify this, because when you have variable in the numerator and in the denominator, the same variable, you would subtract your exponents. All right, so when we do that, you're going to get 2x raised to the 5/2 power minus 3x raised to the 3/2 power plus, and then this one we would keep it as 4 over the square root of x, or 4 over x to the 1/2 power. Typically what you want to do with simplifying with exponents is you want to get rid of your negative exponents whenever possible. So like I said, you could use quotient rule on this, but when you end up doing bottom times derivative of the top minus top times derivative of the bottom, and then you combine like, or bottom squared, and then when you combine like terms and simplify, you're going to end up with this right here. So this is just a much easier way of being able to handle this problem. Now, if your denominator was, for example, square root of x and then plus 2 on the outside of the square root, then you cannot simplify in this manner because you have more than one term in your denominator. All right, so on this one, we've got multiplication in between here, so that is going to be a product rule where this is the first and this is the second function. So product rule says we're going to have the first times the derivative of the second plus the second times the derivative of the first. And then we can distribute here. That will give you 42x squared plus 35. We can multiply this together, which would be 84x squared plus 35x minus 24x minus 10. And we can combine like terms then. The 42 and the 84 would give us 126x squared. You have a 35x minus a 24x, which was 11x. And then we have our 35 and our minus 10, which would give you 25. All right, so that would end up being your derivative. Now, once again, remember what we are calculating. Always remember what your derivative represents. This is simply telling us what the slope of any tangent line on this curve is going to be at a particular x value. That's all this means. All right, so then the next one, we've got 5x squared times this right here. And so you might be thinking of product rule. Well, product rule could be used in this situation, but because there's a 2 right here in front of the x, it actually involves a technique that we have not come to yet called chain rule. And so we're not going to be able to use product rule in this situation. Now remember, when you have a negative exponent, that is the same thing as saying 5x squared over 2x minus 1 raised to the positive 1 power. So this actually would involve using our quotient rule. So the quotient rule is going to be bottom times derivative of the top minus top times derivative of the bottom, which is just 2, over the bottom squared. So if we distribute in the numerator, you're going to get 20x squared minus 10x. Then we've got a minus 10x squared all over 2x minus 1 squared, which we now combine like terms, giving us 10x squared minus 10x over 2x minus 1 squared. And yes, we could factor a 10x out of the numerator, which would give us 10x parenthesis x minus 1. However, it really doesn't benefit us any because nothing's going to cancel with the denominator. So I'm just going to leave it in this format right here. All right, and then we have one more problem here with quotient rule. So we're going to apply this. Go ahead and recite this. Bottom, and just recite it as you're writing it. Bottom times derivative of the top minus top times derivative of the bottom over the bottom squared. All right, so we can distribute. That'll give us 12x minus 15 minus 12x minus 8 over the bottom squared. The positive 12x and the negative 12x will cancel, and that's going to leave us with negative 15 minus 8, or negative 23, over 4x minus 5 squared. All right, so the next problem is going to ask us for this right here, which is your notation for a second derivative. So that's what we need to find for this particular function, is going to be the second derivative. So we do that by finding the first derivative, and then we'll take the derivative of that answer. So we're going to apply product rule here. So we've got first times derivative of the second plus second times derivative of the first. We're going to distribute, so we get 24x cubed plus 6x squared plus 8x cubed minus 12. I'm going to go ahead and combine some like terms, making this 32x cubed plus 6x squared minus 12. Now that's not actually the second derivative, that is just the first derivative here. And now the second derivative is going to be the derivative of that answer. So applying the power rule here, you're going to get 96x squared plus 12x, and that is our second derivative.